Hi everyone, I'm Dr. Surjit Singh. In this video on Python via examples, we shall talk about linked list as a class. We shall also talk about the reversal of the nodes of the linked list. Let us begin. In this session, we will build the linked list class. We'll discuss its constructor and its print and append methods. We'll also learn about the modification of the constructor to convert a list to a linked list. Finally, we'll discuss the method to reverse a linked list. Apart from queues and stacks, there are many more applications of linked lists. So, we will now develop it as a class. A linked list consists of a linear arrangement of objects of the node class. The data attributes of the nodes are often fairly big. For example, these could be the tuples that contain information about students of a school. We use the next attributes to arrange the nodes like a chain. Beginning with the first node, each one of them links itself to the node next in the sequence, continuing until the last node, which then points to none. The nodes of the linked list maintain the parent-child relationship between them. Node A is the parent of node B and the grandparent of node C. Node D is the child of node C. In this session, we will formulate the linked list class. A linked list like this will become an object of the class. The attribute of the class that points to the first node of the linked list is known as its head. Head is none for an empty linked list. In the videos 18 and 19 of this series, we discussed about the printing of the linked lists. We will now use the same function as the print method of the linked list class. For an empty linked list, output of the print method is none. If the linked list is not empty, the print method will show the data parts of all the nodes. We will make use of this print method after we build our class. Let us now write the steps to create an object of the linked list class and append nodes to it. We call the linked list function to create an object of the class which calls its init method. Within the body of every class, we give a generic name to the objects of the class and call it self. First statement of init creates its head attribute that saves none in the head. Note that the prefix self dot is used for all attributes and methods of the class. Init has only one statement. It returns the reference of this newly created object and we save it as myell in this program. It means that head becomes the attribute of the object myll and we will refer to it as myll.head outside of the class definition. At the moment, myll is an empty linked list. We use the append method to add nodes to a linked list. It finds the end of the linked list and adds a new node to it. We pass its parameter and save it as the local variable data of the append method. As the object myll is calling the append method, self inside the class means the object myll. We create a node with A as its data attribute and save its address in a reference variable child, a local variable of append method. This first time, head of the linked list object is none, so we copy the child reference in head also. With this, we have appended the node successfully to the linked list, so we return from the append method. Let us now append one more node to the list. Once again, we call the append method with b as its parameter this time. It creates a new node object, saves b in its data attribute and saves its reference in child. For all the nodes after the first node, head is not none. So we proceed to find the last node of the existing linked list, which will act as the parent of the child node. For this, we save head in a variable parent. As parent.next is none, it means that it is the end of the linked list. So we do not enter the while loop and save child in parent.next. We have now appended two nodes to the list and the append method ends. Third time we append C. Once again it creates a node, saves its address in child and start with parent equal to head. Inside the loop we move parent to the next node while the node next to parent is present. Next node of B is none, so the loop terminates and parent is now the tail of the existing list, which is its linking point with the child node. So we copy the reference of the child node in the next attribute of the parent node. Now that we have appended the child node at the end of the existing linked list, the append method ends. Node C is the new tail of the list. If we append another node to it, C will be its parent. We end the program after the printing of myll object of the linked list class. We must understand that this print is a method of the linked list class and not the print statement of Python language. We can obtain a linked list from a list. This is possible by modifying the init function of the class, which takes a list of values as the parameter. For example, 190 is the list that will produce a linked list object as shown. We name it here as list, which on printing gives this output. Parameter listVal of the init method is optional as it has a default value. If the list parameter is missing, listVal becomes an empty list as the default parameter. This produces an empty linked list. If the list parameter listVal is present, it becomes a local variable of init method. Before processing the list items, we create a node with data 0. This is purely a temporary node that we create to make the program simple. We save its address in self.head. Prefix self dot has been used to make head an attribute of the class. This means that the head is not a local variable of init method. We save it in tail also, which is a local variable of init. Appending the first item in a linked list requires a different programming code segment that involves change in the head of the list. For this reason, we added a temporary node 0 so that the first val of the list produces second entry in the linked list. Now we iterate over all the items of list val and save them one by one in loop variable val. In each iteration, we append val to the linked list. We create a new node with val as its data attribute and save its reference in tail.next. This links the two nodes. We then move tail to save the reference of the new node. In the next iteration of for loop, val becomes 9. We add another node to accommodate this val, save its reference in tail.next and make it the new tail. In the last iteration, val is 0 and we link this node also with the linked list and come out of the loop. Finally, we move head to its next node. This discards the temporary node, which is then cleared in the garbage collection cycle. The init method ends. We save the reference of the newly created object in list. Head is the only attribute of the object of the linked list class. We print it for our satisfaction. We can also append a few more nodes to it and print again. Let us now write the method of the class to reverse a linked list by reversing the next attributes of all the nodes without disturbing the nodes and their data attributes. Let us print the given linked list before defining the reverse method. We will process all the nodes one by one. After reverse, every node will break its link with its child node and will point to its parent node. Node at head is 1. It is the starting node and therefore it does not have a parent node. This means that instead of pointing to 9, it will point to none. So we save none in a local variable and name it parent. We name current as the loop variable. Node at head is the starting value of current. In each iteration of the loop, we will reverse the link between current and parent nodes. The pair of pointers, parent and current, will then move right in a while loop till current passes out of the linked list. In every iteration of the loop, next attribute of the current node will change such that it starts pointing to its parent. But we cannot do it at this stage because we lose reference to the child of the current node. In other words, node with data 9 will become unreachable. So, before breaking the link between the nodes 1 and 9, we must save the reference to the node 9, that is the child of the current node, in a third variable. We call it child. It saves reference to the next of the current node for future use. The three reference variables, parent, current, and child, will move right in every iteration of the loop. We can now change the next attribute of the current node such that it points to its parent. We will now move the three pointers variables, taking care that we do not lose the reference to any of the nodes of the linked list. Presently, parent refers to none. Now that none has got another reference, parent can refer to some other node. So we change parent such that it now refers to the current node. After this, we are free to change the current node. We change it such that it now points to the child node. This is the end of the first iteration of the while loop. In the next iteration, child gets reference to the node that is next to the current node. All the three pointers have now moved to their new positions. We now change next attribute of current node so that it now points to its parent node. This gives us the second link reversal between the nodes. Once again, we can satisfy ourselves that we have not lost reference to any of the nodes and we are ready to move the three pointers by one more step. Parent shifts to position of the current node and then current shifts to the position of the child node. In the next iteration, child node shifts by one more step. We then revise the next attribute of current node. Once again, parent moves to the current and current moves to the child node while the child node shifts in the beginning of the next iteration. Child now becomes none. After this, we change the next attribute of current node to point to its parent node. Next, both parent and current nodes shift. Now that current is none, we come out of the loop. At this stage, the order of all the nodes has been reversed. We move head to the position of the parent node, which is the starting node from the other end of the linked list. The reversal of the linked list is complete and we come out of the reverse method. Only the head, that is the attribute myll, stays. Print method of myll now confirms that we have been able to reverse the order of the nodes of the linked list. In this session, we defined the linked list as a class. Head is none for an empty linked list. We then talked about the append method. We modified the constructor to convert a list to a linked list. Finally, we discussed the reversal of a linked list. I hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.